Hey, good morning, guys. Assalamu alaikum. Welcome back to Inspire Teens, grade 12 physics. Physics/chemistry. In today's lesson, we'll be continuing and probably ending our final lesson of rate of reactions, right? I really want to get into it quickly so that we can do as many questions as possible. We're going to finish up the question that we didn't finish last week, as well as start, let's hope, 2 to 3 new questions. Okay. Firstly, if the screen is a bit unclear, I do apologize. My connection is not the best currently. Okay, but we hopefully I hope that it's somewhat doable and that you guys can see, because unfortunately there's nothing I can do about my connection right now. But yeah, we'll try and have the lesson continue either way. Okay, so rate of reactions is what we discussed, right? We're not going to go through this, revise everything again, but yeah, hopefully you guys understand the theory and that it makes sense. If you guys do have any questions, please ask them or message me or let me know if you don't understand anything. Okay, so yes, we did this question, which we are going to read again. Okay, and I'm going to try and I guess zoom in a lot so that if it's blurred, that you guys will probably be able to see somewhat, hopefully. Okay, so question 5, the reaction of calcium carbonate, CaCO3, and excess dilute hydrochloric acid, HCl. So if you see this word excess, by the way, in rate of reactions, please don't think that we're going to be using Rice table. If you've learned Rice table, okay, this excess is not the same excess that we deal with in acids and bases, or it's not the same excess that we deal with in like stoichiometric calculations that we deal with. It is, okay, but we don't have to worry about it in rate of reactions. Okay, in rate of reactions, that's not what they want to test. They don't want to test excess and limiting reagent and all of that, right? They're not testing that concept. It's just the type of reaction that happens is one with excess, okay, but the values that we will be given will always be the values that actually react, okay? So if you remember, the only place, right, you can only use your molar ratio with things that actually react, okay? Like if you know the exact amount that reacts with a certain amount, that's when you can use the molar ratio, okay? And that's the information that will be given or asked from us, okay? So the excess, that is not a problem, is not something we have to deal with in rate of reaction, okay? So excess dilute hydrochloric acid is used to investigate one of the factors and affects rate of reaction. The balance equation is as follows, okay? CaCO3 2HCl gives us CaCl2 plus H2O plus CO2. The same mass of CaCO3 is used in all of the experiments, and the temperature of the hydrochloric acid in all experiments is 40 degrees Celsius. The reaction conditions for each experiment are summarized below. So what was compared here in our reaction was the surface area or the state of division, right? We went from granules, lumps, and powder, right? We used 3 different ones where we put the order of them. Powder is the highest surface area, granules is the second highest, and lumps is the smallest surface area. Okay, then we discussed for this investigation, write down the dependent. We said the rate of reaction. Generally, the dependent variable for all of these is the rate of reaction because that's what's being tested, right? We are changing other things and seeing how they affect the rate of reaction. Okay, and then the independent, the one that's being changed in this instance was the surface area or the state of division, right? We use different surface areas. Okay. The carbon dioxide gas produced during the experiment A is collected in a gas syringe. The volume of gas is collected and measured every 20 seconds, and the results are obtained as shown. Okay, we can see this graph, right? So this graph is given to us, and we can see the production of CO2 gas in the form of a volume versus time graph. Okay, we can see that the volume is increasing, which means it's a product being formed, right? Let's just maybe clarify here, right? These are product graphs. How are we going to do this? Okay, we can just write it for now. So because it's increasing, this is most likely the formation of a product. I'll copy it over to that one. And this is a reactant graph because we can see that it's being used up, right? It's decreasing. Okay, and the most important thing that we need to remember, again, just to revise from these graphs, is that, okay, it's not like the most important thing, everything is important, but an important thing that we need to remember is the gradient, okay, because what does the gradient give us? The gradient indicates to us the rate of reaction. So that's why we learned and we discussed whether the gradients were increasing or decreasing. So that would tell us whether the rate of reaction is increasing or decreasing. So these are 2 product graphs and these are 2 reactant graphs, right? So whatever the product or reactant for that specific chemical equation might be, okay, that's the one. That's what we're talking about. So yes, this is a product graph, and that's evident here. We can see that CO2 is a product, right? And we can see that it's increasing. So it's a product graph. Okay, cool, done. Okay, so yes, we can see that they're given us. So what you need to note, what's important for rate of reaction is generally we need to look out for. So for example, in this graph, right, this is the actual amount of CO2 that's formed. Okay, why am I saying the actual amount that's formed? Because remember, when it comes to excess reactions, not everything reacts, okay? Because whatever is in excess, some of it is going to be left over afterwards, okay? Most of it is going to react, but some of it's going to be left with afterwards. So, but not all of it reacts. That's the main thing, okay? So what's important to understand what is actually used up and what actually forms. So whenever we have a graph, you should understand that that graph is showing actual values from the so-called experiment that was carried out. Okay, so we can trust these values. These are actual values when the experiment was happened, whatever English. Okay, so in this case, this is the actual amount of CO2 that is formed. So we can actually use this value, okay, and convert it into moles, and then we can use that amount of moles and use it across the molar ratio for the chemical equation. Okay, whereas for example, okay, I'll tell you something. This excess dilute hydrochloric acid, okay, this is it here. It's volume of 500 and concentration of 0.1, for example. I cannot use that values to get the moles of HCl. The reason I cannot use those values to get the moles of HCl is because not all of the HCl is reacting, right? Please note that the chemical equation, in all chemical equations, you can only get the moles with whatever reacts, whatever actually reacts and whatever actually forms. Okay, you cannot use the entire excess amount to get the moles of HCl because not all of it reacts. This reaction only represents the amount that actually reacts. So the excess is not considered in this equation. So that's why I cannot use these values of HCl right now because it is in excess. All right, so I don't know of this 500 centimeters cubed, how much actually reacted, I don't know. Okay, so I cannot use it right now. That's why I turn to the graph. Okay, because the graph tells me this is actually how much formed of CO2. So now I know, okay, that's actually how much formed of CO2. If I can convert that into a mole, I can get the moles of CO2, and then I can split it, or I can convert it to the other moles using the molar ratio across this chemical equation. Okay, so then they discuss, okay, I'm not going to discuss all of this again, but we're just going to go to the last question, right? 5.6. Okay, 5.6 says, assume that the molar gas volume at 40 degrees Celsius is 25.7 decimeters cubed per mole to the -1. Calculate the mass of CaCO3 used in experiment A. Assume that the molar gas volume at 40 degrees Celsius is 25.7 decimeters cubed per mole to the -1. Calculate the mass of CaCO3 used in experiment A. Calculate the mass. Okay, so they want us to calculate the mass of CaCO3 used in experiment 1. Okay, the mass of this guy. If we look at this graph, okay, this graph is the carbon dioxide produced in experiment A. So we know the exact amount of carbon dioxide produced in experiment A. Okay, so it's this amount, it's this 500 decimeters cubed. Okay, 500 centimeters cubed actually of carbon dioxide gas which is produced. I have the molar volume, the molar gas volume. So this is taking place at STP. So I can use the formula. N is equal to V over Vm. I have to convert the 500 centimeters cubed to decimeters cubed. It's 0.5. Let's write it with units. Because decimeters cubed is the SI unit. We have to divide by 1,000. So this is going to be 0.5 divided by the molar gas volume. Molar gas volume is 25.7. Okay, the molar gas volume, the molar gas volume, let me get the memo second. Okay, and this gives us an answer of the moles of CO2. Sorry, we should probably label it, all right, so that we know what we're working with. This is moles of CO2. Okay, the moles of CO2, we get an answer of 0.0195 moles. Okay, this is the moles that we get for CO2. Okay, and we know that this is the correct amount because this is actually what was formed, because we use the graph for the actual information of what was formed. So now I know, if we go back to our little equation, we know that this guy, I think we can just get rid of these things. Okay, we know that this guy has moles of 0.0195 moles. So once we calculate this value, we can then use molar ratio, right? We want to go from here to here because we want to know the mass of CaCO3 that was produced. So we want to go from CO2 to CaCO3, and it's a 1-to-1 molar ratio. So the moles will also be 1-to-1. So let's write that out. We'll write moles of CO2 is to moles of CaCO3 is a 1-to-1 ratio, which is therefore a 0.0195 moles to a 0.0195 mole ratio. So therefore, the moles of NaO3 is, CaCO3 is 0.0195 as well. So now we want to calculate the mass of CaCO3. And if we have moles, okay, we can use this formula. N is equal to big M over, M is equal to small m over big M. Mass in grams over the molar mass. And I can substitute. So 0.0195 is equal to the mass in grams divided by the molar mass. The molar mass of CaCO3, you can use your periodic table. But if I had to guess, never totally look at the memo, it is 100. And we can multiply that. We get the mass of CaCO3 that was used as 1.95 grams. Okay, so I just want to try and remove the confusion of excess and limiting reagent and that in most in the rate of reaction, right? So yes, it's important to consider, right? It's not like it's just totally ignored, but you'll see the values that you are given are generally always the values that react, and there's no need to do a Rice table or however else you work with limiting reagent or excess. You just need to use general stoichiometry, right? But it's important to understand how it works, okay? So just keep in mind, what do we keep in mind? We cannot use those values of HCl because the HCl is in excess and we don't know if all of it reacted. However, we can use the information from the graph because that is definitely what reacted. That is very important. Okay, so that's that question done. 1.95 grams CaCO3. That's what was used in the equation. Okay, what I'm going to do for those of you who perhaps struggle with stoichiometry, I'm going to leave a link. We're not yet done with stoichiometry with the grade 11s. In fact, we're currently busy with it, but I'm going to leave a link to the playlist once it's done so that you guys may revise grade 11 stoichiometry if you really want to, right? Okay, so that's that question done. Let's have a look at the next question. Okay, we're going to try and do 3 questions. November 2021, question 5. The reaction of 15 grams of impure sample of calcium carbonate, CaCO3, with excess hydrochloric acid, HCl, of concentration 1 mole per decimeter to the -1. Again, don't worry about the excess, right? Don't let it scare you. Okay, something that is important, however, that we will work with is impure and pure. Okay, but the excess, again, it's not something that we should be calculating in rate of reaction. Okay, sorry again for the blurry. I hope that you guys can still read it decently. Okay, so yes, it reacts with this excess hydrochloric acid with concentration 1 and is used to investigate, surprise, surprise, the rate of a reaction. The balance, so that's going to be our dependent variable if they ask, right? The balance equation for the reaction is as follows. CaCO3 plus 2HCl gives us CaCl2 plus H2O plus CO2. It's the same as the previous one, right? The volume of CO2 produced is measured at regular intervals. A sketch graph representing the total volume of carbon dioxide gas produced as a function of time is shown below. So this is the same thing, similar to the previous one, right? We have a graph showing it's a product graph, right? Remember, the gradient gives us rate of reaction. Okay, so this is a product graph. The gradient gives us rate of reaction. Okay. The gradient gives us rate of reaction. It's just showing how CO2 is produced over time. And what's important about this is these are actual values. Okay, this is the correct values of how much is actually produced, because we have to be careful for that word excess, right? Because when we use something that's in excess, not all of it is going to react, right? If you remember from limiting reagent questions from last year. Okay. So that's very important. So yes, let's look at the next one. 5.1. I'm not going to write the answer, but define the term rate of reaction. Okay, I'll give you what the memo says. The memo says rate of reaction. Any one of the following you are allowed to give. The change in concentration of products or reactants per unit time, or the change in amount or number of moles or volume or mass of products or reactants per unit time, or amount or number of moles, volume, mass of products formed or reactants used per unit time, or the rate of change in concentration, or the amount of moles or the number of moles, volume, or mass. Okay, so easiest one is probably change in concentration of products or reactants per unit time. Straightforward one, you just give that one and you'll get your 2 marks. Give a reason why the gradient of the graph decreases between T2 and T1. So let's have a look at this. Right, this is why I taught you those graphs with the different types of gradients, and you need to understand when the gradient is increasing and when the gradient is decreasing, right? So here we have this shape initially, right? This is let's we have this shape initially. Okay, it doesn't start that high. Maybe it's there. Then it goes on to be this shape. Okay, so if you remember correctly, this is an increasing gradient. This is actually, you can see this the slope is increasing, right, as we go along. But here the slope is now decreasing. Okay, and that's actually generally what happens in reactions. Okay, initially you'll have an increasing rate of reaction. Rate of reaction is just increasing. That's because we are using up the reactants. Okay, so the concentration of the reactants are strong initially. Initially, the concentration of the reactants is high, But once we start using up those reactants, the concentration of those reactants decreases. And remember, if we decrease concentration, we decrease the rate of the reaction. Okay, it's almost as if initially we have a lot of particles to react. So we react, and the rate of reaction is increasing because the concentration of the reactants initially is high. But once we start using up those reactants to form products, the concentration of that reactants start decreasing. So let's try and do that graphically. Okay, let's just say we have this many reactants to react. So once the reaction starts occurring, right, the reaction rate will be high because there's a high concentration of reactants. But once they start being used up to form products, right, they start being used up to form products, product. Eventually now you can see the concentration of these things are decreasing. Okay, so that's what we mean, right? That's why the reaction rate starts off high and then it slows down, because now the concentration decreases, which would result in a lower concentration, right? If there's a lower concentration, remember, according to collision theory, the less particles there are, the less particles there'll be to collide. So the rate of reaction would be super slow. Okay, so yeah, just keep that in mind. So they say between T1 and why the gradient decreases between T2 and T3. So the gradient decreases between T2 and T3 because the rate of the reaction decreases. How many marks is this for? It's for 1 mark. So you can say rate of the reaction . Rate of the, yeah, so here's it here. The rate of the reaction decreases, they give you the mark, or what you could also say is the concentration of the reactants decrease. Okay, that's actually the reason as to why the rate of the reaction is decreasing. The rate of the reaction is decreasing because the concentration of the reactants is decreasing. Okay, so that's why the gradient decreases between T2 and T3. Okay, and we have to understand this type of shape, right? It's in the notes. So number 5.3, changes in the graph between T1 and T2 are due to temperature changes within the mixture. Is the reaction exo or endothermic? So between T1 and T2, this is a bit of a different style question, but you should be able to use your logic to answer it, right? So between T1 and T2, that red part of the graph. Let's get rid of this, and this. Okay, between T1 and T2, there are some sort of temperature changes. So we can see a rapid increase in the rate of reaction between T1 and T2, right? The curve is increasing. You can see the gradient is getting steeper and steeper, which means that the rate of reaction is increasing. Okay, so in order for the rate of the reaction to increase, right, they said it's a temperature change. In order for the rate of the reaction to increase, this has to be an increase in temperature. That's the key thing. So this temperature change wasn't a decrease in temperature, it was an increase in temperature. Okay, so again, the term between T1 and T2 are due to temperature changes. Temperature changes, this has to be an increase in temperature because the rate of the reaction is increasing. If the rate of the reaction was decreasing, it would be a temperature decrease, but it's a temperature increase. So is the reaction exo or endothermic? It would have to be exo, because if the temperature increased, that means that there has to be a releasing of energy. That's why the temperature is increasing. Energy is being released, or heat is being released. That's why the temperature is increasing. So therefore, it is an exothermic reaction. Okay, so this one just requires you to use a bit of logic. 5.3.2, explain the answer by referring to the graph. So you can say that the gradient becomes steeper on the graph. Okay, the gradient between T1 and T2 is an increasing gradient. Okay, it's becoming steeper. Okay, that means that the rate of reaction is actually increasing because gradient gives us rate of reaction. Okay, and that means that the temperature has increased. Okay, meaning or average kinetic energy of the particles increased, meaning it's an exothermic reaction. Okay. Yes, let's look at 5.4. The percentage purity of the sample is 82.5%. Calculate X, okay, the value of X on the graph, assuming that the gas is collected at 25 degrees Celsius, take the molar gas volume at 25 degrees Celsius as 24,000 centimeters cubed. So we'll have to convert that to decimeters cubed. So calculate the value X on the graph, assuming that the gas is collected. Okay, so they're giving us molar volume, so we can use N is equal to V over Vm. So it's not happening at STP specifically, but they are giving us the molar volume at the specific temperature, so we can use it. Okay, so what is X on the graph? Let's just go back to the graph and let's see. X on the graph is the volume of CO2 being produced. It's the final volume, right? Because you can see that this is where the graph, this is where the reaction ends. So they want us to calculate the final volume of X that is produced, the final volume of CO2 gas that is produced. Okay, the final volume of CO2 gas that is produced. And they're telling us that the percentage purity sample is 82.5%. So what question is this? This is question 5.4. Remember that percentage purity is equal to pure over impure times 100. And we said that pure is what actually reacts. Pure is what reacts. Impure has impurities. Okay, so it's what reacts plus, I like to call it like dirt, okay, extra. That's not going to take part in the reaction because it's not the pure, whatever the sample is. So what is the sample that's impure? The sample that's impure is 15 grams of calcium carbonate. 15 grams of calcium carbonate. So this percentage purity is for calcium carbonate. Okay, and it was given to us that the percentage purity is what? 82.5%. So 82.5 is equal to, so when percentage purity is given, you can work backwards to calculate the pure sample, because pure over impure, we know that the impure sample is 15 grams, so we can calculate the pure grams. Okay, that's the thing. Okay, so here we can divide by 100, multiply by 15. So 82.5 divided by 100 multiplied by 15. So this gives us the value of the pure in grams. Pure is equal to 12,375 grams. Okay, so this is what we can do when we have percentage purity. So percentage purity, they give you the percentage. So we can say that percentage purity is equal to pure over impure multiplied by 100. So I equated the percentage. 82.5 is equal to pure over impure. So pure over 15, right? They told us that the impure sample of calcium carbonate of 15 grams, okay, the 15 gram impure sample of calcium carbonate is used in this reaction. 1 second. Okay. 15 grams of impure calcium carbonate. So that's why in the question they said the percentage purity of the sample is 82.5%. So that's how I worked it out. So now I know the pure. Okay. So by the way, when they say 15 grams of impure calcium carbonate is used, that does not mean that this is 15 grams. That's incorrect to say that this is 15 grams. This is the calcium carbonate, but whatever's in the reaction always represents the pure amount. Okay, the pure amount is what reacts. Okay, this impure sample contains this amount of CaCO3, whatever it is, okay, which we actually worked it out. We worked it out to be 12,375 now. So this is 12,375 grams. The pure sample is 12,35 grams. So whatever else is left, what is it, like 2,625 or 2,725, 625, whatever it is, that's the impure, that's the dirt that's not going to react, right? Remember, what's going to react in this reaction? It's calcium carbonate, right? So the calcium carbonate is the only thing that's going to react with HCl to give us CaCl3 and H2O. So whatever else is above the impure sample, whatever else is contained with CaCO3, that's not going to react. Okay, so only the 12. So that's why you see initially, that's why it's important for us to understand, we couldn't use this 15 grams initially. You cannot use it. You cannot convert this to moles and get the moles of CaCO3 because it's impure. The only things you can use in this reaction is the pure sample. Okay, and that's why they gave us the percentage purity. That's how we got it. That's how we calculated it. Okay, so now we know the pure is 12,375. So now we know that 12,375 grams of CaCO3 actually reacted. So now we can convert this to moles and then get the amount of CO2 that was produced, because that's ultimately what we want. So we're going to convert this guy to moles. So we know the pure grams. Remember that N. So we're going to calculate N of CaCO3, the pure sample, okay? The pure CaCO3 is equal to mass over molar mass, which is equal to 12,375 divided by the molar mass of CaCO3 is 100. So this gives us the moles as when you divide that by 100, you get 0,0,12. You can round it off, but I'm not going to round it off, right? In these sections, I would recommend keeping at least 5 decimal places to keep the accuracy of your answer high. Okay, so the moles of CaCO3 that reacted is now this. We converted the mass to moles. Now we can compare the moles of CaCO3 to the moles of CO2, and we know that it's a 1-to-1 ratio. So it's a 0,12375 mole is to 0,12375 moles. So they have the same moles. Now we can convert, this is volume, okay? We can convert this into, so we can convert, what is it? C is equal to N over V. No, N is equal to, so if we want to get the volume of CO2, we're going to use N is equal to V over Vm, which is equal to, we have the moles of CO2. So 0,12375 is equal to the volume, which is what we want, divided by the molar volume. So by the way, this is in centimeters cubed in the graph, so we'll need to give our answer in centimeters cubed. So in the memo, they use centimeters cubed in the equation. I'm not comfortable doing that. I'd rather convert it to decimeters cubed. So there's 24,000 centimeters cubed. We're going to divide it by 1,000. Okay, to give our answer in decimeters cubed, which is 24 decimeters cubed. Okay, so I'm going to divide this by 24 and then I'll convert back to centimeters cubed, no problem. I get 24 times 0,12375, and I'm getting a volume of 2,97 decimeters cubed, right? So if we want to convert it to centimeters cubed, which is what's in the thingy, one second, sorry. Okay, yeah. So you multiply this by 1,000. So this is equal to 2,970 centimeters cubed. Okay, and that's our final answer of the volume of CO2. So it just comes down to using the formula, right? And what actually reacts. That's the most important part. We have to consider what actually reacts. Okay, that's very important. And in this case, so the impure sample is not what actually reacts. The impure sample of 15 grams, not all of it reacts, right? We calculated that 12,375 of it reacts. Then we converted that into moles, the 12,375, and then we used the molar ratio to convert it to CO2, right, to get the moles of CO2. Once we had the moles of CO2, we could convert the moles of CO2 into a volume. Okay, let's have a look at 5.5. How will the reaction rate change if 15 grams of pure sample of CaCO3 reacts with the same HCl solution? So now, instead of having 13.375 or whatever it is, grams of pure CaCO3, now they're saying if all of it was pure, if it was 15 grams of pure CaCO3, what would happen to the reaction rate, okay, if it reacts with the same amount of HCl? And the answer is increases. Okay, you can guess it. So you cannot say it increases because it has a higher concentration, because CaCO3, right? CaCO3 is a solid. Okay, so when you add more solid, okay, you are basically not increasing the concentration, you are simply increasing the number of particles. Okay, so CaCO3 is a solid, so when you add more of it, okay, into the same amount of HCl, you are definitely going to increase the reaction rate, but not because you are increasing the concentration, just because you are increasing the number of particles present for the HCl to react with. So it would result in more effective collisions, right? So use the collision theory to explain your answer in 5.5. So you can say that there are more calcium carbonate particles. Okay, therefore there are more effective collisions per unit time. More particles have sufficient kinetic energy. Okay, this is only for 2 marks, so you can say, so you don't have to mention the more particles have sufficient kinetic energy. You can just say that there are more particles of CaCO3. Therefore, there are more effective collisions per unit time. Therefore, higher reaction rate. Okay, cool. Let's move on to the next question. Okay, SUP 2021. Okay, 2 experiments, 1 and 2, are conducted to investigate one of the factors that affect the rate of reaction. Okay, common type of example, dependent variable rate of reaction. Okay, and that affect the rate of reaction of aluminium carbonate, AlCO3, Al2CO3, with excess hydrochloric acid, which is HCl. The balance equation for the reaction is that. Okay, the apparatus used is shown below. Okay, so hydrochloric acid, this is a common apparatus where you have the syringe, which actually the gas that formed, which is CO2, the gas that forms is expelled into this tube and fills up this syringe. Okay, so yes, reaction takes place here. Okay, gas that's formed goes up into the syringe, and we can measure it because it pushes the syringe back. Okay, the reaction conditions used for each experiment are shown as follows. So experiment 1, we have 100 centimeters cubed of 1.5 mole per decimeter. So this is volume, this is concentration of HCl, reacts with 0.016 moles of Al2CO3. So this is moles, right? So that's like the amount that's mixing. Granules at 25 degrees Celsius. In experiment 2, we have 50 centimeters cubed of 2 moles per decimeter to the -3 HCl, which reacts with 0.016 moles of Al2. Okay, so it's all the same, right? Granules at 25 degrees Celsius. So the main thing that changes is this. The concentrations differ. Okay, so the concentration in the first one is 1.5, and the concentration in the second one is 2 moles. Now, they do change the volume, but that won't affect the rate of the reaction, because the amount that you use, okay, is not going to affect the rate of the reaction, right? It's an aqueous solution. Okay, so the amount that you use is not going to affect it. The concentration is important. Okay, when it came to the previous example, the amount affected it because we were dealing with a solid, right? So there was more particles of that solid in that defined space, right, to react with the same amount of HCl. In this case, the amount of volume doesn't matter, because if the concentration differs, that's the main thing that is going to affect the rate of reaction. That's why when we did the factors that influence rate of reaction, one of them, we didn't discuss one called volume, because the amount that you choose to use does not affect the rate of the reaction. Okay, but the concentration of that given sample, however much of it you have, that is something that plays an important role in the rate of reaction. So in the second one has a higher rate of reaction, okay, because it has a higher concentration, right? So that's the main difference. Okay, define the term rate of reaction, the change in concentration of products or reactants per unit time. Now, 5.2, using the experimental setup above, state the measurements that must be made in order to determine the rate of this reaction. So the fact that it's a rate of reaction, one of the things that must be measured is definitely time, right? You need to measure time to see how long this reaction takes, right? That would give us the rate of the reaction. Okay. And the other thing would be using the experiment. So you can either say the time, right? So that's the first thing. You can either say now you need to find a way to measure, okay, how much Al2 is being used, or the rate at which Al2 is being used. Okay, it's measuring the reactants. Okay, the reactants being used up, measuring the reactants being used up, or the rate at which the reactants are being used up. Or another easier one to mention is measuring the carbon dioxide being produced. Okay, measuring the carbon. So those are two measurements we need to make. We need to make measure of the time. Okay, and we also need to measure the carbon dioxide being produced, or the Al2 being used up, right? So that we can compare it to time. Like we can say, okay, this much carbon dioxide is being produced according to this time, type of thing. Okay, so that's that. So those are two things. Use the collision theory to explain how the average rate, reaction rate in experiment 1 differs from the average rate of reaction in experiment 2. Now let us compare experiment 1 to experiment 2. So you will say experiment 1 has the HCl has a lower concentration compared to experiment 2, okay, which therefore less particles will have sufficient kinetic energy, less particles there will be less effective collisions per unit time, okay, and resulting in a lower rate of reaction. Okay, less effective collisions per unit time, and therefore a lower reaction. Okay. Sorry, I forgot to define it as well for your first mark. So you will say there's a lower concentration, which means that there are less particles per unit volume. Okay, therefore less effective collisions per unit time. Therefore, a lower rate of reaction. Okay, 5.4. The average rate of reaction in experiment 2 during the first 2.5 minutes is 4.4 times 10 to the negative 3 moles per minute. Calculate the number of moles of Al2CO3 that remains in the flask after 2.5 minutes. Okay, so 5.4, let's answer it. Okay, the average rate of reaction in experiment 2 during the first 2.5 minutes is 4.4 times 10 to the negative 3 moles per minute. Calculate the number of moles Al2CO3 that remains in the flask after 2.5 minutes. So for the first 2.5 minutes, okay, we know the rate. Okay, so remember, the rate of reaction has many formulas. Okay, in this case, we're going to calculate the number of moles. We're going to use delta N, delta N over delta T, which is the final moles, which is that they want the amount of moles left over, minus the initial moles divided by the final time, minus the initial time. Okay, so now the rate of the reaction, we know it's 4,4 times 10 to the negative 3. Did I read that correctly? Yep, times 10 to the negative 3. Okay, it's moles per minute. So it's taking place in minutes, actually. And we're measuring moles. So it's in the first 2.5 minutes. So we have delta T, actually, because the final time is 2,5 minutes. And the initial time is 0 minutes. Okay. So because it's the first 2.5 minutes, so the initial time is 0 minutes, and the final time is 2.5 minutes. And the reason we're not converting this to seconds is because the units that they used for rate of reaction is per minute. Okay, then let's do N final minus N initial. So N final is what they want. Calculate the number of moles that remains in the flask after 2.5 minutes. That is N final. N initial is actually how much we had initially. Initially, we had how much? What is this experiment 2? We had 0,016 moles of Al2CO3. So that's initially how many moles we had of Al2CO3. So it's going to be final, which is what we want to work out, minus 0,016. Okay, so we multiply the right-hand side by 2.5. So 2.5 times 4.4 times 10 to the negative 3. So here we get 0,011 is equal to N final minus 0,016. Take it over as addition, plus 0.016. And we get an amount of why am I not getting the right answer? Why are they subtracting it? Try this one more time. Okay, I see why it's getting the correct answer. Okay, so one thing that I want to discuss is that's important for us to note. Okay, it's actually quite tricky. Is the reaction rate of the, if they give you a reaction rate of the reactants versus the reaction rate of a product. So these are reactants, right? Okay, and remember, reactants, they are used up. Okay, then we have products. Okay, and remember that products are formed. Okay, so because reactants are used up, they actually have a negative rate of reaction. Okay, and because products are formed, they actually have a positive rate of reaction. Okay, negative rate of reaction because they've been used up, right? So they're decreasing. The rate at which the rate is decreasing. It's decreasing the amount of Al2 that we have. Okay, so it has a negative rate of reaction. So the amount can be the same, the magnitude can be the same, but it's just negative when it comes to reactants. But when it comes to products, okay, when it comes to products, we have a positive rate of reaction. So in fact, here I was supposed to substitute negative 4,4. The reason for that is it's because Al2CO33 is a reactant, so it should have a negative rate of reaction. Okay, and then when I add this, my N final, which is the final moles, okay, this is 0,005 moles. Okay, so that's the answer. That's the final moles of Al2CO33 that's left over after the reaction has completed. Okay, let's look at 5.5. Calculate the maximum volume of CO2 that can be prepared at 25 degrees Celsius in experiment 1. Take molar gas volume at 25 degrees Celsius as 24,000 centimeters cubed per mole to the -1. Okay, the maximum volume of CO2 that can be prepared in experiment 1. Okay, so we have to use the amounts that are actually reacted. So remember, it's excess hydrochloric acid. So the one that's in excess in rate of reaction, we cannot use that amount in our reaction. Just remember that. The one that's in excess, we cannot use that in currently in our reaction because it's not all of it reacts. But we do know that all of the Al2CO3 react because they tell us that much of HCl reacts with that much of Al2CO3, right? So for this guy, yes, we can convert this. So this is the moles, Al2CO3. That's maybe perhaps what we can do is steal the equation from here. One second, apologies. Okay, and we can re-put it here. We can work with it. So now we know that this much, this is the wrong equation. Lol. Oh no, it's the right equation. Nope, it's the wrong equation. Okay, so let's do this now that we have the right equation, hopefully. Okay, we know that this here has the moles 0.016 moles. Okay, we know that this is what completely reacts, right? Because remember, if one is the excess, the other is the limiting reagent, and the limiting reagent always completely reacts. So this definitely all of it reacts, and this is an excess. So this all of it reacts, right? They want to know the maximum amount of carbon dioxide that can be produced. So we want to use this moles to get the moles of CO2. So we compare the moles of Al2CO3, Al2 CO3, we compare this to the moles of CO2. This is a 1:3 ratio. Therefore, if this is 0.016 moles, this is going to multiply that by 3. Okay, so this here has moles of 0.048 moles. Okay, so the moles of carbon dioxide is 0.048. So now we want to calculate the volume. They want to know the maximum volume of CO2 that can be produced. So we're going to use the molar volume formula because they've given us the molar volume at that given temperature. 0.048 is equal to that specific volume that we want to calculate, divided by the molar volume, which they give us as 24,000, I'm pretty sure. So I'm just going to divide it by 24 because that's it in decimeters. And I prefer to substitute the decimeter value into this equation and then reconvert back to centimeters. So multiply this by 24. It's going to give us our volume is 1,152 decimeters cubed. They specify what they want the answer in. No, they don't. So we can leave our answer like this. 1,152 decimeters cubed. And that would be all, 5.5. Okay, so that makes sense a lot. That is a question. So unfortunately, we'll have to end there because obviously the time is up. We don't have time for more, but oh, did we do 2 questions? Oh, we did 2 questions. That's great. I thought we did 1 question. So doing 2 questions is great. So then let's just finish on this one because this won't be too long, right? Just want to do that one. Let's last one. It's like more theoretical than anything. But yes, okay, this is this question. Please do ask if you are confused. But this is how you would answer this question. The main thing in this is general stoichiometry, right? It's not anything complicated. You're using basic stoichiometry to answer these questions. You just need to understand that the excess part, right? You can't use the excess value immediately in the equation because not all of it reacts. What you have to use in the equation to get the moles is what actually reacts. So let's just quickly go through this, right? Learners use the reaction of a sodium thiosulfate solution with dilute hydrochloric acid to investigate several factors that affect the rate of reaction. Again, very similar, same thing in everything. Dependent variable, rate of reaction, rate of chemical reaction. The balance equation is that define rate of reaction, the change in concentration of products or thingies, what do you call them? Or reactants per unit time. Okay. 5.2, the results obtained in investigation 1 are shown in the graph below. Graph of reaction versus concentration, reaction rate, concentration, dependent variable, rate of reaction. Conclusion that can be drawn from the results. Here we can see that the higher the concentration, the higher the rate of reaction. That's the conclusion, if that's what they ask, that's the conclusion that can be drawn. Rate of reaction increases with an increase in concentration, or rate of reaction is proportional to concentration, you get your 2 marks. Okay, let's have a look at this. Investigation 2, the Maxwell-Boltzmann distribution curves A and B below represent the number of particles against kinetic energy for the reaction at 2 different temperatures. Okay, the key here says that the particles that undergo effective collisions are after P, right, after that line P. What does the line P represent? That we know would represent the activation energy, right? Which curve AOP was obtained at a higher temperature. So remember, when it's a higher temperature, we're looking for a graph that's, what did we say? The graph like flattens out. Let's see what we said. The graph becomes flattened, right? So we're looking for the graph that's flattened out compared to the other, and that would be B. So B takes place at a higher temperature. Explain in terms of collision theory how an increase in temperature influences the rate of reaction. At a higher temperature, particles move faster or have higher kinetic energy. More particles or molecules have sufficient kinetic energy, right? There are more effective collisions per unit time, therefore, which results in a rate of reaction increasing. Let's look at investigation 3. The potential energy diagrams X and Y below represent the reaction under two different conditions. Okay, give a reason why curve Y differs from curve X. So this is clearly potential energy versus reaction, course of reaction graph. This clearly shows us that Y used a catalyst, okay, because it doesn't go all the way up. The activation energy 6 centimeters cubed of that much. 100 centimeters cubed of 0.2 moles per decimeter HCl reacts with that much. Okay, you guys can do this percentage yield question, right? Please go ahead and practice this. I'll leave the memo at the end, but yeah, let's call it there. Practice an example on percentage yield, practice more examples on rate of reaction. I hope that these lessons were beneficial and that you guys understood rate of reactions. Please let me know if you have any questions. Cool. Thank you guys so much for joining. Alaikum.